Hi everyone. I've been getting a lot of requests to solve one specific question. I don't know, maybe it's an assignment problem. I'm not sure. You'll have to try it on your own. But I thought there were one question in particular was quite interesting. So I thought I'd just clear it out because many of you had asked this. Okay, so I just logged in and I found so many questions. So the problem is that the circuit is a simple op-amp based circuit that's shown here, which has both positive feedback and a negative feedback. And you're supposed to find out what are these inverting and non-inverting voltages, steady state voltages, Vx and Vy. And also you're supposed to find out what is the power delivered by this independent voltage source, 4 volt voltage source, and also the power delivered by the op-amp. So the question many of you had asked is, how do you calculate how much power an op-amp is delivering? So to answer that, keep in mind an op-amp is an active circuit, right? So it is like an amplifier, like a ideal voltage amplifier with an infinite gain. The model for this op-amp is something like this. So anytime your op-amp is driving some resistor, it's going to draw some current out of it. Okay, so that current has to come out from the output of the op-amp, and the output of the op-amp is nothing but a voltage source. Okay, it's a controlled voltage source. So therefore, if the current is going to come out of a voltage source, then it's delivering some power. And it can even deliver or absorb, but normally it tends to deliver power. So all we need to do is to figure out what is the total current coming out of the op-amp and what is the output voltage of the op-amp. Then you have the power that the op-amp is delivering. And also another obvious way of looking at it is there are resistors in the circuit, and there is also one independent voltage source. Okay, if there is any voltage across the resistor, then there will be some finite power dissipated across the resistors. If the resistors are dissipating power, power is conserved. If you're losing power somewhere, then that power has to be supplied somewhere else. Okay, so there are only two elements which can do that. One is the voltage source here, and another one is the op-amp here. Okay, so that's it. So we'll figure out what are those numbers. It's a very simple problem, so I thought I'll discuss it. So step 1, when you're given a problem with both positive and negative feedback, identify which feedback is dominating, whether it's negative feedback that's dominating or positive feedback. So immediately you can see it's a DC voltage source connected between output and the inverting terminal. As far as small signal is concerned, DC is like a short. So if you change this voltage by delta V, this node will also change by the same voltage, because the voltage difference between V minus and V naught is fixed at 4 volts. Okay, V naught minus V minus is given to be 4 volts. That is always fixed. So therefore, delta V, if I change my output by delta V, the change in the inverting terminal will also be delta V. So the gain here is 1. The feedback factor is 1 for the negative path, for the inverting path. For the non-inverting path, which is the positive feedback path, the gain is 3 by 5, right? So it is some value less than 1. So therefore, we clearly see that negative feedback is more than positive feedback. So I can say that this circuit overall will be a negative feedback circuit. Now it's a very simple problem. Once you know it's a negatively feedback circuit, all you need to do is just equate the inverting and non-inverting voltages. So Vx will be equal to Vy, and first thing immediately that you can see is the voltage between V naught minus V minus is 4 volts. Since V minus and V plus are same, okay, the voltage across the 20 kilo ohm resistor will also be 4 volts, right? So it's given V naught minus V minus is 4 volts, and V minus is equal to V plus, so that will also be equal to 4 volts. Okay, now V minus equal to V plus is forced by negative feedback, because we said the circuit is a negative feedback. V plus is forced to be equal to V minus. That's it. The moment you know the voltage across the resistor, you know everything else. So you know the current flowing through the resistor, that will be 4 volts by 20k, which will be 0.2 milliamp. So 1/5 of a milliamp, so which is 0.2, and that same current will flow through the 30 kilo ohm resistor, and the voltage drop across the 30 kilo ohm resistor will be 0.2 into 30, which comes out to be 6 volts. So that is node voltage Vy. So that is same as node voltage Vx. The node voltage Vx will also be at 6 volts. Okay, so that's the first part of the problem. So they asked what is Vx and what is Vy. Both of them will be 6 volts. So now next step, we are supposed to find out the power dissipated in the circuit. So there are 3 resistors, and we know the voltage and currents through all the 3 resistors. So we can easily find out what is the power dissipated. So let's start with P20K. For the 20K resistor, I know the voltage across it is 4 volts and the current through that is 0.2 milliamps. Okay, so the voltage drop across the 20K resistor is 0.8 milliwatts. Okay, 4 into 0.2 is 0.8, and the voltage drop across the 30 kilo ohm resistor, it's 6 volts is the voltage drop, and the same 0.2 volt current flows through it, a 0.2 milliamp current flows through it. So you get a power dissipation of 1.2 milliwatts. Okay, so it's V into I. I'm just doing V times, I know the voltage across it and current through that, so I'm just computing those powers. Then for the 10K resistor, the voltage across it is 6 volts, but the current through that is 6 by 10K. So it's 6 volts upon 10K, and this is 6 into this will be 0.6 milliamp. Okay, and the power across this will be 3.6 milliwatts. So the total power dissipated across the 3 resistors is, if you add the 3, you get 1.2 plus 0.8 is 2 plus 3.6 is 5.6 milliwatts. So this is the total power dissipated across the 3 resistors. I think I've written these values here. Okay, so I think there is some mistake in the calculations here, but that's okay. So 4 volt divided by 20 kilo ohms is 1/5 of a milliampere, which is 0.2. Yeah, I think that's fine. So there is some calculation errors here. So this current is 0.2 milli and 0.2 milli. That's fine. We have already done this calculation, so I'll just ignore this part. So the total power dissipated at the 3 resistors is simply 5.6 millivolts. So I'll call it PR is 5.6 milliwatts. The next thing is to find out what is the power dissipated or delivered by the 4 volt voltage source. Now we know the current through the 10 kilo ohm resistor, which is 0.6 milliamps. The same current has to flow through the 4 volt independent source as well, right? So it's they both are in series. The input current into the op-amp is 0. So now if you see the 4 volt, I've just isolated the 4 volt supply here, the independent voltage source. Current is flowing into the positive terminal. Okay, so generally when you connect a voltage resistor through a voltage source, current flows out of the voltage source, meaning current flows away from the positive terminal. So in that case, we will say voltage source is delivering power. But in this case, since current is flowing from plus to minus, we will say the voltage source is absorbing power. So if I ask you the power delivered by the 4 volt source, I'll use a negative sign to show that it is actually absorbing power. So the voltage is 4 and the current through that is 0.6 milliamp. So the overall power dissipated is minus 2.4. Minus 2.4 is the power delivered. Power dissipated or power absorbed by the voltage source is plus 2.4. So the total power dissipated in the circuit will be the power dissipated in the resistors, which totally turned out to be 5.6 milliwatts minus, you'll have to add it with, because voltage source is also dissipating power, you'll have to add plus 2.4. I've just maintained the convention. So you add all the dissipated powers and subtract all the delivered powers. So if you subtract it, you get minus of minus, so which will be totally 8 milliwatts. Okay, so that's the total, yeah. Okay, so that's the total power that is dissipated from the in the circuit. So the total power dissipated is 8 milliwatt. Now power is conserved, right? If someone is dissipating this power, it is being supplied by someone else. The only other block present here is the op-amp. So the op-amp, the power delivered by the op-amp will be 8 milliwatts itself. That's it. So you can just add up all the powers and find it out. Or there is other very simple way. You just have to find out what is the voltage and current flowing through the op-amp. So that will also give me the information. Okay, so the voltage across this resistor is 4 volts, and we just saw the voltage at the node Vy is 6 volts. So the total output voltage V naught is simply the sum of these two. So I can just I'm just drawing the circuit here for simplicity. So the circuit looks something like this. So this is the 30 kilo ohm resistor and 20 kilo ohm, and we know the voltage across this is 4 volts and the voltage across this 30 kilo ohm resistor is 6 volts. So the total voltage, the output voltage is 10 volts. Okay, so the op-amp's output voltage is 10. So this node voltage here is 10 volts, and the current that the op-amp is supplying is nothing but sum of the current flowing through this resistor and the current flowing through the voltage source. So that will be 0.6 plus this is 0.2 milliamp here, sorry. So 0.6 plus 0.2 milliamp, okay, so that will be 0.8 milliamp. So that's the total current that the op-amp is supplying. It's supplying 0.8 milliamp. One half, a part of it, 0.6 milliamp goes through the voltage source and 0.2 goes through the resistor. So the total current that the op-amp that is supplying here is 0.8 milliamperes. Okay, so now if I see this, the output, I've just drawn the equivalent model for the op-amp. The voltage is 10 volts, the current being drawn it is 0.8 milliamps. So you just take product of voltage into current, you will simply get 8 milliwatts. I'm sorry, I had some calculation mistake initially. So it turns out to be 10 into 0.8, which will be 8 milliwatts. Okay, so that's it. Thank you.